All right. So maybe let's just state this here. Like changing electric fields give us magnetic fields, and that amounts to the same saying as moving charges. So moving charges give us magnetic fields, and of course that amounts to well, what follows from it is that if you have currents, electrical currents, then you will have magnetic field. So every time, everywhere you have an electrical current, you will have a magnetic field. And there are three equations for the magnetic fields due to the current carrying wires that you need to be familiar with. If you are in the calculus-based physics, then you saw the derivations, and these equations should be already known to you. And if you are in algebra-based physics, then I'm about to introduce these equations to you. So first thing is straight wire. So if you have a wire that goes like this, and there's a current I that flows through it. If you move a certain distance away from this wire, now note that this distance needs to be perpendicular, and let's call it R. Then you can calculate magnetic field at this specific point here by using the following equation. So you will have B equals mu naught times I over 2 pi times R. So in this specific equation here, I is the current, units would be amps, R is just the distance from the wire, but I'm going to write perpendicular distance from wire. And because it's a distance, this would have units of meters. Mu naught is a constant, and this is 4 pi times 10 to the minus 7th units are Teslas times meters over amps. B is the magnetic field. Magnetic field, and it has units of Teslas, or just T. All right, so now if you were to draw this magnetic field around this wire, then you would use your right-hand rule. So from right-hand rule, you can determine the direction of and the shape of the magnetic field. Take the thumb of your right hand and point it in the same direction in which the current flows. So point it in this direction. And then curl your fingers. And the way your fingers will curl will be like this. That would be the direction of the magnetic field. So if you're here, current flows in this direction. Point your thumb in this direction and then curl your fingers. Fingers will curl like this, and if you're here, your fingers will curl like this. And so this would be the magnetic field around the wire. It's circular. And at different locations, it will have different value. The farther away you move from the current, the weaker the magnetic field. Excuse me, and the closer you get to the wire, the stronger the magnetic field. And this equation here is the same as this one. So the equation for the straight, the magnetic field due to the current that runs along a straight wire. And this page here is taken out of your worksheet. So the next thing that we have, let's maybe label this as 1, is the second one here. Next thing that we have is the magnetic field at the center of the loop. So now suppose that you take a loop and Well, you take a wire and you bend it into a loop, that you get something like this. And then you run a current into this. So I flows in, flows around, all the way around, and then it flows back out of the loop. You will get a magnetic field that will be just like the magnetic field of a straight wire. That is, suppose you're here in this little section. If you want to determine the direction of the magnetic field, you will take your thumb and point it in the direction of the current and then curl your fingers. Your fingers will curl like this. If you move this way a little, you will get a magnetic field that does this. If you move here, you will get a magnetic field that does something like this. I think I still maintain sort of a picture here. If I'm over here on this side and the my finger, my thumb points in the direction of this arrow, then I would have to curl. Fingers would curl in this way. All right, so maybe I'll do one more. It's a little tricky to draw that. So anyways, so there's that. Now what I have here is that the magnetic field points comes out of the center. So the magnetic field comes out of the center. Let's see if I could sort of draw that. So it comes out of, that's not bad. It comes out of the center. And then it loops around. And it goes below. And it goes below this whole loop. Now, let's look at it in, so this is a 3D, or at least my attempt at 3D. I'm going to write here that this is 3D. This is a 3D picture. But I think it'll make a little more sense maybe if I draw it in 2D. So what I'm going to do is the current flows in this direction, loops around, circular path, and comes back out. So this is I, comes back, and so the current flows like this. Now this is a circle, so there's a certain radius associated with it. There's a radius r that I have here, and let's use little r. And the magnetic field here in this specific case, what I would have is if I take the thumb of my right hand and I align it in the direction in which this current here flows, and I curl my fingers, then what I would find is that the magnetic field comes out of the page here. I would put a little dot and goes into the page here. Comes out of the page here, goes into the page here, and then I'll do a few more. Maybe I'll do them here. So it comes out of the page here, and goes into the page here, comes out of the page here, goes into the page here. And of course, the magnetic field is not just present at the spots where I drew something in blue, but the magnetic field is present everywhere. I just happen to draw something at these specific locations. So, well, the equation for the magnetic field at the center. I'm going to give you an expression for the magnetic field, but only at the center of this loop, so right here, is that the magnetic field B is equal to mu naught times I over 2r. R is the radius of the circle, so I'm going to put now, the rest is going to come in black color, so R is the radius of the loop, I is the current, and B is the magnetic field. And then the third one we have is a solenoid. So I'm going to draw 0.3. Here's a solenoid. So the wire comes in and then it loops around like this and it keeps going. Well, this is not the best picture of a solenoid. Well, let's give it another try. So what if I did this? Suppose that I draw this. Let's do it. Why not? Let's do it. So here's a single loop. we already know how the magnetic field here would look like. So as the current flows in this direction, the magnetic field would look like this. And here in this location would look like this. And then so on and so forth all the way around. But let's draw a second loop directly above it. So here comes the second loop, and it loops around like this. Back out, the current flows in, the current flows back out. Here's the current. Due to the current in this wire, in this little section here, the magnetic field would point like this, out and in under, and here out of loop and in under. And if these two loops are close enough to each other, the magnetic fields will actually overlap. So what you will have is that the magnetic field comes out, overlaps with the one below, combines with it, goes back under, goes back here, connects with this one, and this will do the same thing. So the loop comes up, overlaps with the next one, goes under that loop, comes back up here. So what I will get is that if I have these are two separate loops, but suppose that I have one wire, and this wire just happens to have a loop like this. So the current flows in, loops around, and comes back out. What I would have then is that the magnetic fields of every single loop here would overlap, so that on the outside the magnetic field would look like, let's see, if it goes like this, then it actually would, so the magnetic field of this loop would overlap with the next one, overlap with the next one, overlap with, how many do I have? 1, 2, 3, that's tough. Yeah, maybe this one. So all of these magnetic fields here would overlap, overlap, overlap. That would go under, go on the inside, come back out, and here. So that this would be the direction of the magnetic field on this side. And of course I would have magnetic field everywhere else. I would have magnetic field up there as well. Back goes under and goes here, and so on and so forth. And on this side I would also have magnetic field. In fact, I would have magnetic field really everywhere. So I could simplify it and just draw it like this. Here's a solenoid. The wire comes in and then it just loops around. So it keeps looping, loops, loops, loops. All of these are loops until eventually it manages to come out somewhere here. So the wire comes out. So current flows in and the current flows out. Then I would have a magnetic field here that does the following. And depending on how this current actually how this wire actually turns, the magnetic field would either point down or up, but let's just say it points down like this, and then I would have maybe another line here, maybe another line here, and these lines would then loop. I would have a loop here, I would have a loop here. Oh, look at that, it came back to the same one. There we go, that's better. This one would come back here, and then this one would come back up here. And in fact, at this point, I could say this is north and this is a south pole. In any event, this would be a solenoid. All right, so maybe in red, this is a, so is this. These are solenoids where you have one single wire and this wire just loops around. This is the shape of the magnetic field of a solenoid, and the equation for the magnetic field of the solenoid is V equals mu naught times I over L times N. So L, that would be length of the solenoid. Right, so L is the length of the solenoid in meters. I is the current. Mu naught is a constant that I already gave you somewhere up there, but I guess I'll state it again. So this is 4 pi times 10 to the minus 7th, and then units are teslas times meters over amps. And N is the number of loops you have in a solenoid, number of loops. All right, so now we have all of these equations explained, and they are also on your worksheet. So we have this equation, which is the equation for the magnetic field due to a straight wire. We have this equation, which is the equation for the magnetic field at the center of a circular loop. And we have this equation, which is the equation for the magnetic field inside of a solenoid. And we just make the assumption that the magnetic field on the inside of the solenoid stays constant everywhere on the inside of the solenoid. So it's not just that this is the magnetic field at the center of the solenoid, this is the value of the magnetic field everywhere on the inside of the solenoid. N prime, by the way, it's just, see, there's a little n prime here. That n prime, let me put it here, let's just put it here. That n prime, that's just the number of loops over the length of the solenoid. That's all it is. It's sort of the density of the loops. Okay, so I'm going to clear up all of this stuff and I'll solve a few simple problems from this worksheet. Okay, so let's do number one. Number one from this worksheet. Let's see what it says. 10 amps is flowing through a straight wire. Calculate magnetic field, produce 2 centimeters away from the wire. Then draw the magnetic field. So here's the wire. Here's the current I. It's 10 amps. The question is, what is the value of the magnetic field 2 centimeters from the wire? So you can pick any spot on the wire and then count a distance that is perpendicular to the wire. And this would be your R, which is 2 centimeters, so 0.02 of a meter. And then this is your point of interest, so this far away, what is the magnetic field at this specific location? And of course, note that this magnetic field would be everywhere along this line here. And as long as it's 2 centimeters away, it would be, magnetic field would be whatever it would be. Same thing on the other side, as long as it's 2 centimeters away in this direction here, you would have value of the magnetic field the same everywhere here. And in fact, everywhere along this three-dimensional cylinder, if you could picture it. So, but I'll get back to that. So anyways, find the magnetic field at this point here, 2 centimeters away from the wire. The equation that I will use is the first equation that I have there. So magnetic field B equals mu naught times I over 2 pi times R. And I have everything that I need. So let's plug in the numbers. Mu naught, that's 4 pi times 10 to the minus 7th divided by 2 pi times the current, which is 10 amps, divided by the distance, which is 0.02. And so in this case, pi goes, this goes, that's just 2. This 2 actually goes away with this 2. Oh, that becomes interesting. So what I have here is just 10 divided by times 100. So this is times a 1000. So what I'm going to end up with is 10 to minus 4th Teslas. That's it. Okay. So the magnetic field is just 10 to the minus 4th T at this specific location. Now let's finish the problem, because it also says here that what is it? Draw magnetic field around the wire. So let's do that. So if the current flows in this direction, this is the direction of the current, take the thumb of your right hand and align it, make it point in the same direction, and then curl the fingers of your hand, and you will see that the magnetic field points like this. It comes from under the wire, then it just loops around like that. It goes this way. Maybe I'll do one more here, like that. All right, I think that'll do. If you want to, you can draw more of these magnetic field lines, but I think 2 will do. So that's number 1. Let me add something to it. So this is a 3D picture here, but let's draw it in 2D. So let's say that this wire points like, say that the wire just runs like this, and here's the current I. I could draw the magnetic field. I could indicate the direction of the magnetic field a little differently here. So if the current points to the right, then the magnetic field above the wire is going to come out of the page. Points out of the page, then I have to draw these. So this is your conventional symbol for out of the page, direction for out of the page. And then below the wire, it points into the page. So I'm going to put a little X's. This is a conventional, so this X indicates the direction into the page. Into page. All right, so you could also do that. These two pictures are equivalent. It's just that this is a picture in 2D. So let's do, you should do number, let's see, the second problem is what you should do. So you should pause the video now and do the second one. And I'm going to do, I think, number 3. So here's third problem. 2 parallel wires are separated by 2 centimeters. Let's draw a picture here. Here's one wire. Here's another wire. And I know the distance between them, it's 2 centimeters. One wire carries 2 amps in the positive X direction. So let's say this is the one. I equals 2 amps. Carries the current in the positive X direction. And the other one carries a current in the negative X direction, but it's -3. So here's the other one. And that would be 3 amps in the negative X direction. So let's call this I2. Let's call this I1. What else do we have there? Calculate the magnetic field at a midpoint between the 2 wires. So what I want to find is, well, if this distance here is 2 centimeters. Was it 2 centimeters? Yeah. Then the distance to the middle is 1 centimeter. This would be 1 centimeter. And of course, this is also 1 centimeter. And I want to find the magnetic field at this location. So the question here is, what is the magnetic field at the center there? Now each wire is going to contribute to the magnetic field at the center. And the total magnetic field is going to be, I guess I'll put total, but we could also call this the net magnetic field, or equivalent magnetic field. Anyways, it's just going to be B1 and then plus B2. But let me put this in the vector notation so I don't have to worry about the signs. Plus B2, and then one of them may be positive, the other one may be negative, or maybe they're both positive, maybe they're both negative. So let's determine the directions of these magnetic fields. So B1, which would be due to I1. Right, so magnetic field at this point here, determined, set up by current I1 would be, well, if the current I1 flows in this direction, so if this current flows in this direction, points like that, then take the thumb of your right hand, make it point in this direction, the direction of this arrow, curl your fingers. If you do that, you're going to find that the magnetic field comes out of the page and then goes into the page at this location. So I'm going to back this out and I'm going to put little X. And this is B1. Now, maybe we'll do B2 in red. Let's call this, redraw this in red here. So here's a current in this wire that flows in this direction. Let's determine the magnetic field that this current sets up at that center here, center point. So take the thumb of your right hand, make it point in the same direction in which this arrow points. Curl the fingers of your right hand and you will see that the magnetic field here comes up from under the wire, goes around, and then goes into the page on the top. So I'm going to back this out, and that means that the magnetic field due to the bottom wire, B2, also points into the page. Which means that they will just add up. So the total magnetic field, the magnitudes, are just going to be B1 plus B2. All right, so I have that. Now what remains to do is to actually figure out the two magnetic fields. So the total magnetic field is going to be, well, what I have is magnetic field from one wire plus the other wire. So this would be mu naught times I1 over 2, where's the equation? 2 pi times R1 plus mu naught times I2 over 2 pi times R2. But this is R1 and this is R2, both the same. So what I can do is I can write that the total magnetic field is equal to mu naught divided by 2 pi R, and then I have I1 plus I2. So first one was I1 was 2, so this is 2 amps plus the second one 3 amps. And that's that. I'll plug in the numbers, but then, so this is 4 pi times 10 to the minus 7th divided by 2 pi times 1 centimeter, which is 0.01 of a meter, and then times 5. Oh, look at that. I forgot pi. There should be a pi here. 4 pi 10 to the minus 7th. So pi goes away, 2, 2, I'm left with 2. So this would be 10. 10, and then I have 100, so this is 1000, so this would give me 10 to the minus 4th Teslas. Oh. All right, so that's number 3. Okay, now you can do numbers 4 and 5. And I'm going to pause here.